So now my question is, how much time can I borrow? Right? Look at D2. D2 has gone into phi 2. Correct? How much of time can I borrow there? Right? First of all, what is time borrowing? What is the exact definition of time borrowing? It is the following. Okay, I have my phi 2. D2 was allowed to change somewhere here. Right? This is all contamination delay and indeterminate states. Okay? This time after phi 2 rises is called T borrow. How much of time? Ideally, if it was a flop, you would have had to ensure that the change happens before the rising edge itself. The latch is allowing you to borrow some time into the steady state of the clock. How much time is that is the question. Okay, so D2 has to get sampled by that latch L2, right? So when should D2 settle? And what's the violation window, by the way? This is the violation window. Yeah? Yeah. So it has to settle before the violation window. Correct? So this time is, what is this time? In the violation window, setup time. Setup. Correct? Now if you look at phi 2 and phi 1, right? So phi 1 is here, okay? This is 0 and then it goes high somewhere here. What is this time? This is basically half a clock period, because from phi 1 to phi 1, rising edge of phi 1 to rising edge of phi 1, it is Tc, right? From rising edge of phi 2 to rising edge of phi 1, it is basically half a clock cycle. Just think about it. Suppose this were basically zero non-overlap, right? Then what would happen? The duty cycle would be 50%. Both phi 1 and phi 2 would be on for Tc by 2. That's what I'm showing here. This time is Tc by 2 and this time is basically T non-overlap. So now what do? You simply add all these components. I have Tc by 2 on one side. I have T borrow plus what? T setup. Because this edge can move all the way till here. There will be no violation even then, right? So in the limit, it is T borrow plus T setup plus T non-overlap. What's the inequality? Greater than or equal to, which implies, right? Now, what happens if there is Q? Yeah? Yeah, so if there is Q, then this clock phi 2 is going to move this way, which means that, let's say it moves all the way till here, right? Which means that my thing can move only up to here. Time borrowing can happen. Setup time, no, not till there actually. Setup time before that edge, right? So now the violation window also moves here. So then this can move only up to here, right? So it's basically it's going to eat up into your setup time, and therefore I will say plus T skew implies T borrow should be less than or equal to, at most you can borrow Tc by 2 minus T setup minus T non overlap minus T skew. Makes sense, right? Suppose the T non overlap was 0, then I would get more time to evaluate my thing, right? If phi 2 had a more on time, I actually have more time to borrow. So T non overlap should eat into your amount of time that you can borrow. Okay, so that's why that's the interesting part where you say that okay, non-overlapping clocks are good, but how much of non-overlapping? Well, if you make it too non-overlapping, then you're eating into your amount of time that you can borrow, and thereby you're going to worsen your clock frequency. Yeah. 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 Skew in phi 1. No, you are saying that what happens? Are you saying that phi 1 becomes like this? Huh? No, but the point is the rising edge of this of phi 1 is never an issue. This is something that you have to get. That's why I am saying first draw your violation window. This is my violation window. So the fact that phi 1 rises early or late doesn't matter one bit. It's only when it falls and samples that it matters. That's the difference between a flop and a latch based design. Correct? Okay, so be very careful about this. Okay. So now what is the whole point of time borrowing, right? Why is it very good? Why is it very good? And why is it that the latch system allows it, but a flop based system does not allow it? Yeah. Sorry? Yeah. Correct. It's not misguiding. With respect to that it is Tc by 2. In the original timing without any skew, that distance is Tc by 2. Skew is eating into that. That's all. Okay? Yeah. So now let's look at this very simple example that we have. Suppose I have a large block C1, okay, and a very small block, okay. On the x-axis, I'm representing how much time it takes to evaluate. Longer C1 means it takes longer time to evaluate. C2, okay. Now I am going to say I will try to design the system with a flop based pipeline, okay, phi and phi, okay. What is the maximum clock frequency that I can run it at, assuming that I am going to put another flop here? Okay, I have somehow partitioned this combinational block which was C1 plus C2. I had a combinational block like this, C1 plus C2, and I made it C1 and C2, and I put a flop in between. What is the maximum clock frequency that I can run this at? Yeah? So my Tc, right, condition should be greater than or equal to what? T PCQ, correct, plus TC1, no, TPC1, no, TPD1, okay, plus T setup. and it should be true even for C2, correct? So what is the only thing I can do? You take max of these two guys, right? TC should be greater than or equal to TPCQ plus TP, I would say simply max of TPD1, TPD2 plus T setup. Only then the system can function correctly, right? What you're doing in a latch based system is I am not going by the max operation. C1 can take more time to evaluate provided C2 is small enough to finish within that clock period, right? So I remove this condition. So if you look at what the condition in the latch based system was, it is basically TPD1 plus TPD2 minus plus what? TPDQ1 plus TPDQ2. This is what we had for a latch system. This is the flop system. So the key difference I told you earlier that the sequencing overhead was not very different for a latch based system and a flop based system. It was T setup plus TPCQ in flop based system. It was TPDQ1 plus TPDQ2 in a latch based system. But what is the difference? This max constraint has now been replaced by TPD1 plus TPD2. It means I can have one combinational block take longer to evaluate, the other one shorter to evaluate. As long as both of them together finish in one clock cycle, I am fine. That's the key difference between a latch and a flop based system. The hard edges of a flop impose that you have to deal with every block within that period. Whereas time borrowing is allowing me to some flexibility. Okay. So now let's look at what is the case I was talking about, where I am not allowed to borrow time across cycles. Okay. So look at this system. I have a finite state machine like this. C1, right? This is QD, right? If you look at this system unrolled in time, okay, this is block C1, this is my flop, okay. If you look at this system unrolled in time like I did earlier, I'll have a flop running at 5, block C1, another clock 5, another C1, this will repeat forever. If it is a flop based system. Now if I put latches also here, the same C1 is repeating over and over and again, which means what I told you earlier is not going to be possible. You can do time borrowing if one block takes time, provided the other block is short enough to finish early. But if it's the same block that is repeating again and again, there's no question of faster or slower. At some point you're going to violate if I borrow across the boundary. Right? So the way to analyze these feedback systems is to unroll it in time and then see what happens. Right? But now your question is, we can come back to that question of what happens if there is clock skew. How come this system can be clock skew tolerant if I cannot borrow across a cycle? The point is the flop is the same. So there is no skew now. See, I can have two different flops with two different clocks and then I can talk about skew. But physically, if it's the same flop, because of feedback, only in time it's getting unrolled. This clock is not 5-1, 5-2. It's the same 5. So therefore, there is no skew to be discussed here. And therefore, in general, latch-based systems are skew tolerant. When you have feedback, yes, you cannot borrow across the cycle, but in that case, there is no skew to be spoken about. It's the same flop or the same latch that you're coming back to. Okay? Any questions here? I'm over time, I know, but I need to finish today. the theory part at least. Any questions here? Okay, so we'll stop here.